Okay, an interaction is when two forces act between two different objects. And the reason they come in pairs is because each object acts on the other. So if I do something to one object, then that object does something to me. That's why there's two forces. Because I apply a force and object 2 applies a force. Okay, so what's an example of this? Pushing off a wall on skates. So if you're on roller skates and you push off the wall, you apply a force forward. So here is you pushing on the wall. Here's your incredibly well-drawn roller skates. So you would apply a force into the wall. Force from you. And then the wall would apply a force back on you. So why do you go backwards? Because the wall pushes you backwards. Yeah. You don't go forwards, you don't go backwards because of you. You go backwards because of the wall. So why does the wall apply a force? Because you applied a force in the first place. So it's kind of a chicken-egg thing. Do you move backwards because the wall pushed you, or do you move backwards because you pushed the wall and the wall then pushed you? If you didn't push the wall wouldn't push you back. But if the wall doesn't push back, you don't move. So it's both of those things. They both exist. You push on the wall pushes of you. Is this the same as what we've done with net force? No. No, this is not net force. Because notice that net force was multiple forces on one object. This is two forces on two objects. One force is from me on the wall. The other force is from the wall on me. So no, these are two forces on two different objects. Not two forces on the same object. Okay, Newton's third law. This one's pretty simple. That is not how you spell every. Every action or force has an equal and opposite force. Oh, so reaction or force. Okay, so what is the reacting force to your hand punching the wall? Any thoughts? So it's going to hurt. But what's the reaction to your hand punching the wall? You punch the wall, the wall punches your hand. Okay. if the forces between us and the Earth and us are equal and opposite, why don't we see the Earth move when we fall? Okay, so every action has an equal and opposite reaction. So if I were to jump off my desk, oh my gosh, shouldn't have worn skinny jeans. There we go. So if I were to jump off the desk, here we go. 3, 2, 1. Hold on, because I'm going to make the Earth move. Okay, so be prepared. Okay, here we go. 3, 2, 1. No one fell out of their seat, so I must not have made the Earth move. So, but I did make the Earth move. So why didn't you see it?
Because the Earth has such a greater mass.
Yes. Newton's second law. F net equals ma. The force that I put on the Earth and the force that the Earth puts on me are the same. So the force from the Earth and the force from me are the same. But they both equal ma. Okay? The force from me is going to have a relatively, so the force on me is going to have a relatively small mass, which means it has a relatively large acceleration. But the force acting on the Earth has a relatively large mass, so it'll have a relatively small acceleration. How small is the acceleration? It's almost zero. If you calculate it, it's like 0.0000001. It does accelerate, but it is so small that you don't notice it. So do I accelerate the Earth? Yes. But do I notice it? No. And the reason is the masses are so different. So yes, the forces are equal and opposite. No, we don't notice it because there's a large mass difference. Okay, last kind of concept-y question here. So if I punch a wall as hard as I can and a sheet of paper as hard as I can, why does one of them hurt my hand but the other doesn't? Okay, so if I punch a wall as hard as I can, it's going to break my hand. But if I punch a sheet of paper as hard as I can, it's not going to break my hand. Why? Right, so it's going to resist change a large amount, right? Which means it can apply a large force. But the paper will not resist change a large amount, which means it can't apply the same force. So even though I'm punching as hard as I can, the interaction between wall and hand is large, but the interaction between the paper and hand So, when you play a force between the paper and the hand, it looks like this. They're small. When you apply a force between the wall and the hand, it's like this. So, these forces are equal and opposite and large. These forces are equal and opposite and small. So if you do a large force, it depends on the other object on what size the force will actually be. Okay? Here's what I want you guys to do for next time. For next time, you need to get your rocket built. Okay? You need to get your rocket made. Remember, it needs a nose cone, it needs fins, it needs a 2-liter bottle to hold the water at minimum. So if you're looking for what do I just need to do to get a reasonable rocket together, that's what you need. You need a bottle that holds the water. It has to be 2 liters. you need a nose cone of some sort, and you need fins of some